Not Xiaojun, but I want to just say a few words about this. So this paper is about gesture typing, which is a paradigm that is a truly innovative, new paradigm that's already on perhaps a billion devices. But if you look at the very first paper, Corolla and I published in Kai 2013, 2003. 13 years ago. The big part of it was about defining the keyboard layout, so the gestures. So the gestures on the given keyboard, on a given layout, will be all well defined and well separated, and so therefore people can learn and remember the shapes better. Therefore, you can get it to a truly shorthand writing, a new way of writing stage. But I would say that's still far from being a reality. So we keep on returning to this topic, that is how we can actually find a layout that is both much more clear, much more efficient, and also much more easier to learn. And unfortunately, those three altogether don't seem to come together easily. And here is another attempt at making it at least easier to learn. Because the Qwerty is just about the most difficult, or in some sense, worst keyboard for gesture typing in terms of defining shapes.
Yes, as you can see here, one reason that Qwerty is pretty bad for gesture typing, you look at the top right corner of the layout, the three vowels, U, I, O, they are placed together. It's called a problem for gesture typing because in gesture typing, you are inevitably cross all the letters, and it's called problem. Here I show you some examples. See, tip and top is the two very common words, and they have identical traces on gesture keyboard. And here for E and on, two very common words. And because I and O are placed together, they have very similar shape, so the decoder often gets confused by which word you intended to include. Here's another example. Need and not, they have very similar shapes. So, because Qwerty is inefficient and inaccurate for typing, there has been a lot of effort in optimizing keyboards. The previous work mostly focused on how to improve the performance, how to improve speed and accuracy. But later we found out that one of the biggest challenges of optimized layout is about learning. We have been using Qwerty for more than 100 years. And we use it on a daily basis. When we have a new layout, users have to spend more time to switch to Qwerty. Even though we know that they will eventually have good performance, they are unlikely to switch from Qwerty to other layouts. And this work will focus on how to improve the learning of the optimized layout. More specifically, we try to see if we introduce some Qwerty constraint. Basically, we try to keep the optimized layout similar to Qwerty. We want to see whether it will improve the learning. And we also want to see, under this constraint, whether we can still get optimized layout. So we look at three kinds of Qwerty constraints here. The first one, we call it Qwerty1 constraint. It is also known as preset Qwerty in previous work. So basically, if we're given letter on layout, its new positions can only be at most one key away from its Qwerty position. We call this position a Qwerty neighbor. So for letter G on a layout, the possible new location for G, possible location are these 8 slots. The second constraint is even stronger. We call it the Qwerty H1 constraint. Basically, the keys can only move horizontally on the same row, and of course, it has at most one key away from its Qwerty position. So for letter G here, it has only 3 possibilities in optimized layout. And the third one is the strongest. So we only do one swap. We only swap a pair of keys on a layout over Qwerty. And these 2 keys have to be Qwerty neighbor. For example, like G and H, one possibility. So we want to investigate under these 3 constraints, can we still get layouts that are better than Qwerty? And we hope that these constraints will help users learn the new layout. And we optimize layout for gesture typing. So the procedure was very similar to what I did in last year's Kai research project. We optimize gesture typing layout for both accuracy and speed. For accuracy, we introduce the gesture clarity metric. It basically quantifies to what degree a given gesture on a gesture on given layout is separated from other gestures. So the higher the gesture clarity, the better the keyboard for gesture typing and more accurate. For details, please refer to this paper. And the second objective is the typing speed. We have a model, we adopt a CLC model to predict the time users need to enter a word, giving its gesture trace. So in this optimization problem, we try to optimize layout for two objectives, speed and accuracy. And more specifically, we want to investigate if we add these three constraints separately, how will it affect the performance and whether it will improve the learning. We run, it's a very typical Pareto optimization program. We have two objectives, and the outcome of the optimization procedure is a set of Pareto optimal layout. And we pick the most balanced one. The one have a balance between just accuracy and speed. And here are the optimized results. So on the one swap constraint, we happen to say that swapping I and J, you will get a layout that has the most balanced value between speed and accuracy. Very interestingly, swapping I and J has some other strong pairing effect we did not expect. For example, I and J, they are next to each other diagonally on Qwerty, and also they happen to be consecutive letters in the Roman alphabet. And also, if you look at these two letters, they have very similar visual appearance. So there's a strong pairing effect. I hope that it might help you to remember, okay, you swap the two keys and then to remember the position. And this is the optimized layout under Qwerty H1 constraint. You can see that we have 16 keys moved to new location. And this is the layout we got under the Qwerty H1, so Qwerty 1 constraint. 22 keys change their positions. And this figure actually shows the performance of its different layout. And the metrics are normalized between 0 and 1. This orange dot indicates the layout that is optimized for clarity only, and we didn't add any constraint. It's basically the maximum clarity value you can ever get. You can see here at the far end of the clarity axis. Here's the layout we optimized for speed only, and we didn't add any constraint. Basically, you can move any keys to any location. And you can see here, Qwerty is at the very low end in both axes. It actually confirms our observation that it's very inefficient and ambiguous for gesture typing. And this is the layout we optimize for both metrics, and you have no constraint. So what you can get is kind of in the middle between speed and clarity. And here's the performance of the three optimized layouts under three constraints.
Yeah.
Interestingly, you can see that the Qwerty H1 and the IJQwerty have very similar performance, and both are better than Qwerty, especially in gesture clarity. So it shows that by swapping only two keys, I and J, you can get this clarity metrics improved by a lot. And we need to look at some concrete examples to get some initial feeling of why it happens. You can see here's some words I showed at the beginning of the presentation. You can say tip and hop. By simply moving letter I to the second row, these two traces are clearly different from each other. On Qwerty, they are identical. And for words in and on, you can see here, you have more separated traces on IJQwerty than on the Qwerty. And this is the gesture traces for not and need, these two words. Clearly, they are more separated on IJQwerty, means that the decoder will more likely to get it correct. So for our theoretical analysis shows that IJQwerty and also other layouts, they have a higher gesture clarity and also higher input speed than Qwerty, but they are all obtained based on theoretical analysis. Next step, we conducted a practical study. The purpose are, first we want to know whether this optimal layout under 3 constraints can improve the learnability. Second, we also want to see whether we observe any performance gain with this new layout. Conducted within the subject user study, and we test the 3 optimized layouts together with Qwerty. And also we pick 2 tasks here. First is the phrase input task. So it basically want to test when you first pick up the keyboard and to enter phrases, whether they will have performance improvement on the optimized layout. The second task is the word repetition task. We pick 20 representative words, and for each word, you enter it 7 times in a row. The purpose is that when you repeat the same word again and again, in the last few repetitions, you will reach the expert mode. And we'll see whether we observe any performance gain at this stage. And we look at the speed measured by word per minute and the word error rate. So here's the result for phrase input task. Interestingly, you can see that for IJQwerty, it has the similar input speed with Qwerty. Static analysis did not show significant difference between these 2 layouts. And both of them are significantly faster than Qwerty H1 and Qwerty 1. It shows that when you first pick up the keyboard, first pick up the IJQwerty, it didn't have any performance degradation. But for other tools, we observe that they actually, although we add Qwerty H1 and Qwerty 1 constraint, they still had the performance degradation with these 2 constraints. And for the error rate, we didn't observe any significant difference between error rate. Because in the task, users are free, so they are allowed to track mistakes and use backspace. And in the second study, for the word repetition tasks, some findings confirm confirm what we observed in the previous study. So let's see, for the first repetition of the word, the first time user encounter the word and enter on the new layout, we can see that IJQwerty and Qwerty, people have shorter input speed than other 2 layouts. It indicates that IJQwerty user didn't slow down when they first encountered this IJQwerty new layout. Starting from the repetition 3, we can see that Qwerty, IJQwerty, so for all of the 3 optimal layouts have shorter input time than Qwerty, means that they are faster. The difference between Qwerty and other 3 layouts are significant here. And here the error rate of error rates of the 4 layouts. You can see here for IJQwerty, it actually has a lower error rate than Qwerty. It's consistent with what we observed by it's consistent with what we showed in the gesture clarity index. You can see that because you move this, you separate these 3 vowels, you actually get separate gesture traits from others. So overall, our study. So in this research, we investigate how we can improve the learnability of optimized layout. And in the meantime, can we still have a layout that is better than Qwerty? And we showed that in our research, we investigated 3 constraints, 3 Qwerty-like constraints, to see whether they will help with gesture typing. We find out that IJQwerty is a pretty easy to learn layout and introduce no performance degradation over Qwerty when you initially use it. And also, this new layout is faster and more accurate than Qwerty when the user reach the expert mode. That's it, the presentation. Thank you.
Please line up in the middle. The mic is in the middle. Any questions?
Michael Groß, University of Hannover. No, I think it's not.
It's on.
Okay. So my question is, you basically allow single swap with the IMDJ, and you get this nice property. What if you allowed a single swap, but between using any keys? So did you look at other constraints, like you expect would be even better? Or
Yeah, so
basically,
yeah, because you have more freedom. Yeah, you have more freedom in that if you don't constrain the Qwerty neighbor. I think at least it won't be worse in this situation because this one is the subset of that new approach. I mean you can swap any two keys right on the layout. So I think we did some experiment that shows that if you swap all the two keys, for the theoretical analysis, it didn't improve much over the IJQwerty. And we can see even in the Qwerty H1 constraint, so Qwerty H1 you have more freedom in getting the optimal layout. You still have a similar gesture clarity and speed over IJQwerty. So IJQwerty is pretty sweet spot. This is the first point. Second point is that if we allow the freely swap any two keys, I think it will hurt learnability. Actually, we did the project last year. In our last year's research, we introduced this Qwerty similarity. So you can move the keys away. We didn't really confine them to Qwerty neighbors. And the case, so the problem that we found that it didn't really improve learning because, like, sometimes when you encounter the key, you don't know the location. So the idea of Qwerty constraint that when you try to look for a key, if you don't find it on a Qwerty neighbor, on the Qwerty position, you will first look at its neighbor, and then if not, you might increase your search radius to the second key. But if you randomly swap two keys, if it happens to be very far away, it will introduce a lot of time in searching for these two keys, and overall, it will add more learning time, more frustrations.
Thank you.
Yeah.
Hi, Tim Pack, Microsoft Research. To some extent, when you're dealing with ambiguity, some ambiguity is worse than others depending on the language model context.
Yeah.
So, for example, high and go is much worse than fit and top, right? Because then you have the context. So, why didn't you guys consider using that as a constraint? The larger, constraint of the language model context. And then the other thing is when you're actually evaluating the word error rate, you're testing on phrases, but are you evaluating on single word recognition? So is it top best for single word without the context?
So for the phrase, it's within context. We use in the test, it's a fully functional keyboard with language model and everything. We just change Google.
Right. But then you can see that there's sort of like a conflation there because of the context.
So I think just move on for the
Okay.
discussion.
I was too excited I forgot why I was giving a few more words in the beginning. I want to say that Xiaojun and I have worked together for many years, but despite free food and other more significant perks at Google, Xiaojun is going to join Stony Brook next year. So that was the reason. To that question, Tim, it's a very complete question. Actually, last year, in our last year's work in defining keyboard gesture typing clarity, we spent a lot of time, a lot of back and forth on that very topic. That is, how do you define clarity if you do consider language model context? We decided to cut it at unigram level. The reason is that if you consider bigram or n-grams, and then there's a next level, like what if we use LSTM? What if we use semantic models? And then the context would change even further. The spaces will just become so complex that it would be very hard to optimize. Maybe you have better ideas. Tell us if you choose to. So, yeah.
Last question.
Yeah, so my question is related to your experiment, where you mentioned that in your experiment, by multiple levels of typing by the same user, the expert behavior emerged out. So what is the limit? When do you see that the expert behavior has emerged out? Because this is a problem which I have been facing with my experiment, and every time I make users repeat the same phrases, the next time they do it faster. So what kind of limitations do you keep in here?
So actually, to simulate expert mode, it's in a second study, which is a word repetition. It's not phrase repetition. Basically, you enter the same word multiple times in a row. So the reason we believe it's simulate expert speed, because if you look at the time you need to enter a word in the repetition, you can say starting from the third repetitions, you kind of reach a ceiling. So it means that at this stage, mostly your performance is determined by your motor ability, not by whether you're familiar with layout, whether you need to search for that. So I think it's a way to, it's approach to simulate your expert mode in a short period of time. So I hope I answered the question. So
yeah. So would you like to say that by repeating a same word for approximately 7 times, the motor speed has been achieved?
Yeah,
the
so
movement time.
Yeah, I think in typing, basically your input time will be constrained by your motor ability and some maybe other like the visual search time and whether you remember the words. So the idea that you repeat the same word multiple times, maybe at the first or second trials, you might still need to do some visual search. But once you repeat the same time in a row, it means that in last few trials, we expect that it will eliminate the visual search time and or cognitive load. Remember the shape, and you will just rely on your motor ability to enter the word. And I think that's what expert will do in the gesture typing. And to test our hypothesis, we can look at the curve of the input speed. You can see that the speed definitely increased in the last few trials, and then actually reach a pretty stable level, which indicates that how to get further improvement after that stage. I think that's confirmed that they probably reached the expert mode at this stage.
So perhaps what he meant is actually just whether that's a mistake, but it's actually done on purpose. It's actually precisely to your point, because people will do better next trial if you do it repeatedly, and we do that to measure what eventual performance people would be able to reach. It doesn't mean in actual use they will reach that faster, but eventually will reach that. But you cannot do that long experiment in order to prove a point. So that's precisely to your point, that is, we want to take the advantage of the fact that people learn faster if you repeat the same motor control pattern. But the clarity would still show the same way. So the idea is that we try to test clarity if you after larger amount of learning. So it's essentially acceleration. That's the idea.
Thank you. Right. Thank you.